All right, let's jump right into this explainer. We are looking at Caldwell 69, or as you probably know it, the Butterfly Nebula. It is absolutely stunning, right? But beyond just looking like a giant cosmic piece of art, this nebula is a massive scientific puzzle. Today, we're going to unpack its bizarre chemistry, the extreme physics involved, and two completely different scientific paradigms that try to explain exactly how this magnificent structure came to be. To kick things off, NASA's astronomy picture of the day asked this really beautiful, thought-provoking question. Are stars better understood for their art after they die? I mean, it really hits the nail on the head. Stars often save their most complex, jaw-dropping displays for the very end of their lives. But what's actually painting this picture? Is it just a chaotic, random explosion, or is there a highly structured force at work? To figure that out, we first need to get a sense of where this thing is. So, Caldwell 69 is sitting roughly 3,400 light-years away from us, right in the Scorpius constellation. It's huge, and it's hiding some intense structural and chemical secrets that we are really just now starting to decode. Because we aren't just looking at a cloud of dust here. We're looking at a wildly dynamic environment where the literal building blocks of the universe are being forged, destroyed, and reorganized all at the same time. Okay, so here is where we hit our first major mystery, the chemistry. Typically, when astronomers look at a planetary nebula, it's kind of a one or the other situation. It's either oxygen-rich or it's carbon-rich. But Caldwell 69, it totally breaks the rules. It actually has a weird mix of both carbon-rich and oxygen-rich materials packed into the exact same structure. For the longest time, this completely baffled researchers. Like, how on Earth, or how in space rather, could two contradicting chemical environments just coexist like that? Well, it turns out the secret is spatial segregation. Imagine a massive, freezing cold cosmic donut, an equatorial torus circling the very center. That torus acts like a heavy shield, protecting all the oxygen-rich molecules from the brutal radiation coming off the central star. But out in the open wings, those big, beautiful lobes of the butterfly, you've got carbon-rich molecules called PAHs, and those are just getting constantly blasted by blistering ultraviolet light. So the physical shape of the nebula is literally dictating its bizarre chemistry. Because of this setup, the whole nebula acts like a giant cosmic laboratory. Deep inside that protected donut shape, scientists have actually found water ice, along with crystalline silicates like phosphorate. But the real game changer? They found carbonates, specifically calcite and dolomite. This was the very first time we ever detected these minerals outside our solar system. Before this, the assumption was that you pretty much needed liquid water on a planet to form carbonates. Finding them floating deep in a dying star's nebula completely rewrote our understanding of cosmic chemistry. And if the chemistry doesn't impress you, the physics absolutely will. Caldwell 69 is one of the highest excitation planetary nebulae we know of. That central star is totally hidden by dust, but we know it's unimaginably hot. We're talking over 200,000 degrees Kelvin. That radiation is so intense that it creates these highly ionized gases, like silicon atoms that have literally had 8 of their electrons violently ripped away. It takes a massive, massive amount of energy to do that. Oh, and meanwhile, that heavy dust torus is expanding outward at about 8 kilometers per second. So yeah, it is an incredibly dynamic environment. Which brings us to the big question. How do you get this perfect hourglass shape? Well, our sources offer two completely different perspectives to explain this. Let's start with this standard astrophysical model. This theory says the shape is the result of gravity, fluid dynamics, and a massive dying star casting off its outer layers. Basically, you're looking at an aging star violently coughing up gas over thousands of years. According to this exploding star theory, Hubble Space Telescope data shows a timeline of at least 4 distinct mass ejection events over the last 2 millennia. The star threw off its gaseous envelopes in these explosive bursts at insane speeds, anywhere from 10 to 600 kilometers per second. But why the wings? Well, the theory is that the dense dust torus acted like a physical corset. When the star exploded, the gas simply couldn't punch through that thick ring around its equator. So it took the path of least resistance, shooting straight up and straight down, which created those huge sweeping wings. But what if it wasn't an explosion at all? That brings us to our second perspective, the electric universe theory. This paradigm offers a completely different mechanism. It totally shifts the focus away from gas dynamics and gravity and instead looks at the roles of electricity and magnetism. The argument here is that if you just treat the plasma of space like a simple fluid, you're missing the primary forces that are actually doing the heavy lifting.
So instead of a dying explosive star, this theory relies on something called Birkeland currents. These are basically invisible, twisting electric currents traveling through the highly conductive plasma of space. In this model, space isn't just an empty vacuum where gas clouds bump into each other. It's more like a vast, interconnected electrical circuit, and the stars themselves are just nodes powered by these massive currents, rather than being powered purely by internal nuclear pressure.
And here's the thing about these electric currents. They don't just shoot in a straight line. As an electric charge flows through plasma, it generates its own twisting cylindrical magnetic field. It literally wraps around the current like an insulated wire sheath. This wrapping effect is what gives the currents such incredible stability across mind-boggling interstellar distances, dragging ionized matter right along with them in a spiral.
You can actually see a similar effect in another nebula, M29. According to the electric universe theory, electromagnetic forces naturally squeeze or pinch down on the center of these currents. It's a phenomenon known as a Z-pinch. When the current gets dense enough, it pinches the plasma, forming these perfect, glowing, nested hourglass shapes. And the kicker? It does this naturally, without needing a stellar explosion or a physical dust corset. So in this view, the Butterfly Nebula is just a brilliant example of a normal Birkeland current in glow mode, pinching down on a central star.
So why does all of this matter? Well, looking at these two distant viewpoints really shows us just how intensely this single beautiful nebula challenges our basic understanding of the universe. On one hand, you have a model driven by gravity, violent ejections, and physical barriers acting over thousands of years. On the other, you have electromagnetic circuits pinching plasma into these incredibly intricate, stable geometries. We're looking at the exact same breathtaking structure, yet deducing entirely different fundamental forces at work. It just goes to show you that space is far from a solved puzzle. Whether you find yourself leaning toward the established kinetic models of stellar death, or you're intrigued by the electrical circuits of plasma cosmology, Caldwell 69 is an absolute testament to the complexity of the cosmos. It leaves us with one incredibly profound question to chew on. Is the true architecture of our universe ultimately shaped by gravity and explosions, or by the invisible threads of electricity and magnetism? Keep looking up, keep asking questions, and we'll see you in the next explainer.